Hey everybody, it's Michael. Today we're going to go over proportioning of concrete mixes and mix design. We're going to do that in a video lesson, so please take advantage of the format. Pause, go back, go forward, rewatch it a couple times, because I'm going to try to move through this in under 10 minutes, and it's a long problem. And that problem is problem 7.9 in the course textbook. And I don't really have enough space here, so please read through that problem, go through the problem statement, because I'm just going to get started right into the answer. All right, so the first step to this problem is to analyze the design requirements or the strength requirements for the mix design. And we're given that the required design strength is 3,000 psi and that a standard deviation of 250 psi is expected. But to get a strength of the mix, we essentially have to look at the statistical data and figure out how to make it so that 90% of the cases will be covered under this mix, and only 10% will be left out. So if we look at this, this is that required design strength given by the problem. And so if we do 1.34 times this standard deviation, will get us to this required strength of the design mix. So that's what we're going to do. So the first equation is the required strength is equal to the compressive strength plus 1.34 times the standard deviation. And for this problem, that equals 3,000 psi plus 1.34 times 250 psi. And that equals 3,335 psi. Now, if this standard deviation were large, we'd use this equation, and we'll just check. So the required strength is equal to the given compressive strength plus 2.33 times the standard deviation minus 500 psi. And in this case, that would equal 3,000 psi plus 2.33 times 250 psi minus 500. And that equals 3,083 psi. So this answer is larger, and we'll use that as our required strength, 3,335 psi. All right, so I should also note that this standard deviation right here, does not require a modification factor. Well, it does. It requires a modification factor of 1, so you just multiply it by 1 and it would stay 250 psi. This is because there were more than 30 samples used for the statistical analysis, and if there were less than that, you would look at the table on page 257 of the book and multiply the standard deviation by the appropriate modification factor. All right, so the next step is to calculate the water-cement ratio, and to do this, we're going to look at Table 1 in Chapter 7, and that table is called Typical Relationship between Water-Cement Ratio and Compressive Strength of Concrete. And so you can see that there's a column that lists the compressive strength from 2,000 to 7,000 psi, and then from there, there's water-cement ratios, which can be based on whether air entrainer was used or not. Now, in this case, in our mix, air entrainer was used, so we'll be looking at the air entrained concrete column. And if you look, we're going to have to interpolate because we're given 3,000 psi has a water-cement ratio of 0.59, and 4,000 psi is given a water-cement ratio of 0.48. So we're going to use basic interpolation to find what this value is at the strength we need. So to do that, it's a basic slope formula. So we're going to have the value we want is equal to 0.59 plus, we calculate this this ratio right here from here versus this. And so we're going to have 3,335 minus 3,000 in units of PSI, of course, and 4,000 minus 3,000. So that's, this value is this distance, this value is this distance. Well, it's not that distance, but it's the ratio, because it's actually this distance and then this distance, but the ratio is the same, and that's what gives us this value. And so we're going to multiply that by the distance between this value and this value. So 0.59 minus 0.48. So if we calculate that out, we're going to get x is equal to 0.55. And I noticed a mistake right away, because this should actually be a minus sign because we're going down in values from here. Right here, this is our initial water cement ratio, but we want to check with table 3 in chapter 7. So chapter 7, table 3. And from there you can see it gives you a maximum water cement ratio by exposure conditions. We see that concrete is exposed to freezing and thawing in moist conditions or deicers as one of the options. And if we go back to our design statement, we see that the design environment is just a pavement slab in Bozeman, Montana, which is a cold climate. So actually, we're going to use this value, which is 0.45, for those conditions, and that's actually smaller than the 0.55, so this is actually the value we're going to use. All right, so once we've found our water cement ratio, we're going to look at the coarse aggregate requirements, and we're given that the nominal maximum size is 2 inches in the problem statement, which means that the maximum size is the sieve size above that, which is 3 inches. And now we need to check if this is okay for the dimensions of the conditions that it's being built to. And so if you go to page 261 in the book, you'll see that for a situation that we have, which is an unreinforced slab, that there's a maximum aggregate size of 1/3 of the thickness of the slab. So if we do 1/3 times 12 inches, which is the thickness of our slab, that's going to equal 4 inches. And because the 3 inches is smaller than the 4, then the aggregate size is okay. So from here, we're going to go to table 5 in chapter 7. That's on page 263. And we're going to get the bulk volume of coarse aggregate per unit volume of concrete. And to get this, we need our nominal maximum aggregate size and the fineness modulus of the fine aggregate. So if we look at that table, you can see that the factor that we need is going to be between 2.6 and 2.8, the fineness moduli for a 2-inch nominal maximum aggregate size. Now when we interpolate, we get a factor of 0.75. This value we just found to find the weight per unit volume requirements of our coarse aggregate. And to do that, we're going to need this oven rotted density, which was given in the problem statement as 120 pounds per cubic foot. And it's a pretty straightforward calculation. It's simply equal to this 120 pounds per foot cubed times 0.75 feet cubed per feet cubed times just a unit conversion of 27 feet cubed per 1 yard cubed. That's a cubed right there. And with this calculation, this gives us 2,430 pounds per cubic yard of coarse aggregate.